Question 1. Clearances. So we can start with a simple model and then build on it. The first thing we have to do when uh, beginning our model is determining what properties of materials we want. So whether we want to assume that the materials are linear or to let them be nonlinear. Also, we have to determine whether we want them to be isotropic or orthotropic or none of the above. This will affect the calculations later. Um, Starting with key aspects of the model needs to include, of course, mechanical deformation, and this mechanical deformation is going to come from uh, pressure from the flow, overall momentum transfer from the flow, vorticity. We have to include centrifugal forces if we're calculating radial clearances. Um, and additionally, we have to include deformation and all the components due to heat transfer, more specifically forced convection. All the components are under some sort of forced convection, whether it be cooling flow or high pressure, high temperature flow within the motor itself. That will affect the overall size of the components. If we want to refine the model further, we can add elastic effects on the materials, whether this be creep just from repeated loading on the blades, or another thing that can be added is in the radial clearances we can add Jeffcott whirling, which is simply the whirling due to a rotational imbalance of the rotor, since it's basically a disc on a shaft, and it will tend to whirl if there is a rotational imbalance. Since no manufacturing process is perfect, then there is going to be wear. Other aspects that we can take into account are transient effects or unsteady effects of the flow. We can also include in our calculation, most likely we would need to include manufacturing tolerances, and all these calculations can be done through computational methods. In this case, there's really no closed form solution for something this complicated, so computational methods, most likely coupled simulations that include CFD and FEA mainly. My example is a machine element design course final project in which we had to design a two-branch, two-stage gear train, and our constraints were the gearbox size, the weight, the torque output to input, and lifetime, desired lifetime. The code was done through MATLAB, and my job was to select the appropriate gearing sizes that would work. The code can be divided into 5 functions. The first one, which was the main function, simply initialized all the global variables, which were the constraints, and its final output was the gearing ratios and the proper pitch sizes. Within this function, there were 4 sub-functions which did all the calculations and all the details. The first function inputted the torque ratio and used this in a for loop with if statements in order to calculate the appropriate gearing ratios that were co-prime to minimize uneven wear, and that did not exceed 10 by AGMA standards. This function outputted all the gearing ratios, and the second function, what it did was check the pitch size of these ratios in order to see that it fitted into the box. The output was all the pitch and gearing ratios that could fit into this gearbox, which was fed into the third function, which calculated all the stresses, all the appropriate stresses in these gears, whether it be surface or tooth root stress. And the output of this function again was stress, and it was fed into the fourth and final function, which used the AGMA empirical correlations in order to make calculations for fatigue and using different material properties, output safety factors, and this was again done with a for loop and a for loop for all the data and an if statement just to verify that the safety factor was not less than 1. And the output was all the ratios that worked with the teeth already sized that gave the appropriate lifetime and that satisfied the constraints. Question 3 on optimization of a turbine blade. Possible objectives of this optimization exercise may be to improve efficiency, and this could be done by maybe reducing tip clearances, improve performance of the blade, reduce wear on the component, to maybe increase its lifetime, or maybe we want to reduce the cost of this component. The necessary inputs for the optimization exercise would be, first of all and most importantly, desired constraints. These constraints may or may not include cost. Maybe the size has already been selected, so it could be size. Maybe the operating conditions are already decided. Maybe the materials already decided as well. The maybe part lifetime has already been decided, and there may also be best practices that we might want to follow, or standards that we might want to follow for specific processes of the component that the component would require. Additional inputs are going to include most likely a parametric model of the blade and surrounding components, just to be able to evaluate its performance if that's what we're trying to optimize, and a given model, physical model of the interaction between components. Now, getting more into interaction of individual components with the turbine blade. The first source of interaction with another component is going to be in the interface of between the rotor and the blade. These two components mate together, and of course if the blade is modified, it is likely that the rotor will either require a modification or will allow room for an improvement. Another source of interaction is going to be the shroud and the blade. In this case, it's not actually, hopefully it's not contact between the two, but in that small radial clearance between the blade tip and the shroud, there is going to be a modification in the way the flow interacts with the components, and thus modification in how these two components behave together. Additionally, and I believe this is one of the more important ones, there would be the interaction between the vanes and the blade. These two components are complementary components. It's more than likely that if one changes, the other one is going to have to change. Question 4. Last year, when I was working with McGill Formula SAE team, we had a very specific method of how we manufactured the firewall of the car. The firewall is basically just a structure that protects the driver from the engine and all the heat that comes out of it within the monocoque. So the method we had beforehand was to make a full manufacture of the monocoque, and then out of a single plate cut out the contours of the inside in order to fit them to make the firewall itself. Now the problem with that is that there is variability in the contours on the inside, so we had to wait for full manufacture of the monocoque first before we got started, and then we had to basically cut it down iteratively and very gradually in order to make sure that it fit the contours properly. And this was a very, very time-consuming endeavor. It took usually about a week to do. And so the idea we had was to, instead of having to cut it to shape to manufacture it already with the shape of the original contour, the nominal contour. And so the way we did that was, or the way I thought of doing that was to machine the foam core of the carbon fiber composite using a CNC and then lay up on it so that it already came out with the final shape once it was cured. And this saved ourselves quite a few hours of work afterwards because we could fit it almost perfectly in at the first time. There were some adjustments that had to be made, but it was nowhere near having to cut a rectangular plate into a very complex contour. So uh, how that was the outcome. Question 5. The gradient descent method builds on the mathematical concept of the gradient, and what the gradient is able to do is, in a real valued function, it is a vector that points in the direction of largest increase, which means that if we take the opposite direction of that gradient vector, we are pointing in the direction of largest decrease, and basically this points in the direction of a local minimum. The optimization of aspect of this concept is basically a minimization problem, and we use a data set to evaluate the gradient and then go towards the minimum and do so iteratively until we reach some sort of convergence if the problem is well posed. In order to optimize a component of a gas turbine engine using this method, we would first have to find a component which has an aspect that needs to be minimized. So, for example, in a turbine blade or whatever other component, this could be weight or cost or heat loss, and we would find the working relationship between this parameter that we're trying to minimize and other constants that we can control to build a data set. On our first iteration, we do this, we evaluate the gradient, and then this points us in the direction in which this would be minimized the quickest, and from there we can iterate until we reach our desired point. Number 6. First of all, compatibility. This is a very important key feature that we should always be looking for. Whether it be backwards or forwards compatibility, is very important to have it, and also to be compatible with different operating systems because different users have different computers. Also, lightweight. A software should not be resource intensive for no reason other than because it was badly developed. Additionally, we have a need for focused functionality. Usually nowadays the trend is that we want one software to do everything, and I don't believe this is the right call or the right direction in which we should move. Different users, as I said, have different computers, and most of the time they have different needs, and each software should cater to specific needs rather than very, very broad ones that they're not able to satisfy in its entirety. Also, we have planned obsolescence. A software should not become obsolete every time a new iteration comes. This is simply a wasteful feature, particularly for the user. Also, we have error acknowledgement and ease of troubleshooting. So usually when the end user walks into an error in a piece of software, they don't really know what's going on, they don't really know how to fix it, and if the software itself cannot identify what the error is, it becomes very difficult to troubleshoot even if you call support or ask for help. Another thing that is very valuable is customizability, particularly with software that offers a broader array of functionalities. As I said before, users have different needs, so a software should be able to remove functionalities or allow the user to select what he wants so that everything else doesn't get in the way. Also, we need clear instruction manuals and good resources for the software. Otherwise, the full functionality is never actually going to come out because nobody is going to understand fully how to use it. And this, adding to this, we also want good syntax for the software. Sometimes you know what you want to do, you know how to do it, but you don't know what the syntax is for the software itself, and this can bring back the experience and slow down your learning curve. Finally, user interface. This is also a very important thing. At the end of the day, everybody uses the software in a computer that has a screen, a keyboard, a mouse, maybe a touch screen if you're lucky, and you want to make use of that effectively and as efficiently as possible.